Okay, a domain. We talk about functions. They have a domain and a range. The domain are the Okay. Let's try this size. The domain are the input values. They're generally the x's. They can have other letters, but these are the numbers that you put into the function, and then you get a value out, and the value you get out is the range. Which are generally y's. Okay. A relation is any kind of relationship between two numbers. And you can describe them as ordered pairs, points on a graph.
Can I just be a formula?
It can be a formula. Okay. So a relation is any relationship. I can describe any relationship I want to. I can say 2 goes with 50 billion, 3 goes with negative 27. It doesn't matter. It's just like I put things together. Coordinate plane. You guys have seen these. It's where you get an x-axis and a y-axis. Okay, and they cross at 0. So it's two number lines put together in a T. And the quadrants are the 4 regions that makes. Record this. Okay, so we have a coordinate plane. The horizontal axis is the x-axis. The vertical axis is the y-axis. Okay. If you have a hard time remembering that, you know how y has like a part that goes up and down. So the y goes up and down. This is quadrant 1, but we use Roman numerals, so it's Q1. This is quadrant 2, so it's Q2, Q3, Q4. In quadrant 1, both x and y are positive because we move positive on the x-axis and positive on the y-axis. In quadrant 2, we're going negative on the x-axis and positive on the y-axis. Quadrant 3, they're both negative. And then quadrant 4 is a positive x and a negative y. All right, so if you're asked to name a quadrant, I have the point T, which is at negative 8, 5, okay? So that's negative, positive. Okay. Simple enough, hopefully. Mapping is a graphical representation of a relationship or a relation. And there are 4 types of mappings, and one of them happens to be called a mapping because they couldn't think of another word, I guess. All right, so you have ordered pairs. So we can put numbers in ordered pairs. When we start talking about identifying functions, this type of mapping is a really easy way to just look at the picture and go, oh yeah, that's a function, or no, it's not. So it's a useful mapping. You probably remember, but a function is a special kind of relation. Okay, and what makes a function special is that each element of the domain, so every x, okay, so each x, if you take an x, it only goes to one y. And that's what makes it a function. Now, it doesn't say anything about the y's. The y's can have as many x's go to them as they want. But the x's only go to one y. Yeah. Oh, pairs. Sorry, I didn't dot my I, and that probably didn't help either. Okay, so each x only goes to one y. And we'll remember the domain is the x's and the range are the y's. So if I'm listing the domain, I usually just put a D for domain. And I list the elements. R for range. And I list the elements.
What's the word up in domain?
Here,
Mm-hmm.
every.
Do we have to put those weird parentheses?
Yes, that's set notation, and the domain is a set. So, I mean, if you just, obviously, perfectly, they're like that. But if you just give me some sort of squiggle, I'll know what you mean. I know they're not easy to draw. But yeah, you do. You end up drawing a billion of them.
I carry away
Okay, to tell if it's a function, I'm going to look at, I have a 10, a 6, a 7, and an 8. I don't repeat any x's, therefore it's not possible that any of these x's is going to a different number than the one it was paired with, right? So there's 10 with 3, but there's no 10 with anything else. Same with the 6. There's a 6 with a -2, but you don't see 6 with anything else. So it is a function. Yes?
So a function basically is when a number doesn't repeat?
Well, it can repeat. So I could have another 10, 3 here, but that's the same. So it can repeat, but what I can't have is like a 10, 8.
Why?
Because that would mean the 10 was going to 2 different numbers, and it's only allowed to go to 1.
Right.
Does that make sense? Yeah. Okay. So I'm just going to, because if I put that in there, then it's not a function anymore. Okay, a table, my domain are all the x's, so it's 1,
Wait, but
2, and 3. Yeah.
There's the same y, though. What's the difference?
Y's, it doesn't matter. I can have 2 different x's go to the same y, and that's okay. I just can't have one x go to 2 different y's.
Oh, okay.
Alright. Okay, so the domain are the x's, the range are the y's. Okay. Each x is only going to its own individual y. 1 y. So there's like, it's not like 1 is going to 3.4 and 7. 1 just goes with 3.4, so it is a function. Okay. Now here's the mapping that I was talking about, how it's useful. It already lists our domain and range elements, so we don't have to list those.
So if there's two lines coming from the same number.
Yeah, you look on this side only. You look at the domain only. The range does not really matter. And I go, okay, that has one arrow. This has two arrows. Okay, this is bad. So this is not a function. Okay, you just look down the domain, and as long as everything only has one arrow, you're good. It's a function. As soon as you see two arrows, it's not a function anymore. When we look at a graph, what we want to do is we want to look down each individual line of the graph. And those are the X, I'm going to call them X lines. So we're, this X line, that's where X is -1. This is where X is 0, X is 1, X is 4. Okay, there can only be 1 point per line. Okay, and in this case, I only have 1 point per line of an X, so yes, it's a function. FOIL stands for first, outside, inside, and last. And it's the order that you multiply in. Okay, so if I have two binomials and I'm multiplying them, I'm going to multiply the first two, then the outside two, then the inside two, and then the last two. FOIL.
So FOIL's just distributing?
But it's the order you distribute.
Oh, true.
So you do the first two, then the outside two, then the inside two, and then the last two. And so if I multiply this out, what I'm going to get is x times x, which is x squared, x times 3, so that's 3x, 2 times x, and then 2 times 3. And then here I have like terms in the middle, so I add those together. So if you don't like FOIL, you can also use a table. And the way that works, it works just exactly like a multiplication table, like back up there on the corner. I'm going to write the binomials like this. X times x gives me x squared. X times 3 gives me 3x. Negative 8 times x gives me negative 8x. And then negative 8 times 3 gives me negative 24. If you use this method, you'll notice that your diagonals line up your like terms. So you're going to add those two together. So I'm going to get x squared minus 5x minus 24. The nice thing about a table is if you need more, like if you have longer things that you have to multiply, you just add extra columns or extra rows, and your like terms will still line up on the diagonals. So that's kind of nice. But it's the same thing. If I had taken this exact same, well, here, I'll FOIL it so you can see it's the same. If I do first, outside, inside, and then last, I get the same answer. Oops. That should be an 8. So it really doesn't matter what method you use. If one seems like it makes more sense than the other, pick that one. Okay, anybody have an opinion? How would you like me to do this one? Foil? Okay. So I'm going to do first. So 3x times 5x gives me the 15x squared. Outside, so that's negative 12x. Inside is positive 10x. And last is negative 8. So I get 15x squared minus 2x minus 8. Since I already did the table for that one. Okay, so on this one they were both positive, so I get 15x squared plus 22x plus 8. Okay, and like I said, the reason tables are nice is if you have larger polynomials, all I have to do is add more columns or more rows. So I'm going to do 2x plus 3, and then I have 4x squared minus 5x plus 10. So this gives me 8x to the third minus 10x plus,
Wait, so it doesn't matter
sorry,
which
10x
one's on the
squared.
top and which one's on the side?
Nope, it does not matter. So that's minus 10x squared plus 20x, and then I get 12x squared minus 15x plus 30. And if you look, again, my like terms are lining up on the diagonals.
So you just basically make the numbers wherever. Just make the numbers wherever.
No, I'm putting them in order, right? So this is 2x plus 3, and this is 4x squared minus 5x plus 10. It doesn't matter which one I put across the top and which one I put across the side. And then each square is, it works like a multiplication table. I multiply these two to get that one. I multiply these two to get that one. So I get 8x to the third plus 2x squared plus 5x plus 30. And I got this 2x by adding these two together. And I get this 5x by adding these two together. If you don't like the table, that's perfectly fine. You use basically the same idea as FOIL. You multiply 2x times each element in the second one. And you multiply 3 times each. It would be the same thing if you had a 3 by 3. You'd multiply the first by all 3, the second by all 3, the third by all 3. So you have to keep just adding more and more arrows. I think personally, for me, it gets visually confusing at that point, and it's easy to miss something. But that's me. I like lines and blocks and everything to be organized. If you like this method better and it works for you, by all means use it. If you like this method better and it works for you, use that. As long as you don't miss any. Factoring. It's basically using FOIL or the distributive property backwards. All right? We have a situation like this. Your first step on factoring is you want to factor out any common terms. And you want that to be the greatest common term, so you're doing the GCF, the greatest common factor. So if I look at 4 and 8, the largest number that will divide into both 4 and 8 is 4. Okay, and then I have 2 A's and 1 A, so I can take out 1 A from each of them. Now if I do that, if I factor out 4A, if I take 4A squared and I take away the 4 and I take away one of the A's, I have an A left. And if I have 8A and I take out a 4, I have 2 left. And if I take away the 1A, there are no A's left. So what I've done is I've looked at the 4A squared and I've looked at the 8A, and I figured out what can divide into both of them. Okay, that part's good. Now I take what I found and I put that on the outside. And then I divide, essentially I'm taking 4A squared and dividing it by 4A. And that's where I got this A. And then I take 8A and divide it by 4A, and that's where I get that 2. Better?
Yes.
Okay. 4x to the third minus 10x squared plus 14x. I'm going to look at the 4, the 10, and the 14. And the largest number that can go into those three numbers is a 2. And then I look at the number of x's. I have 3 x's, 2 x's, and 1 x. So the most x's I can take out is 1. With the variables, it's always going to be the one that has the least. Okay, so I'm going to factor out a 2x. If I divide 4 by 2, I get 2. And if I divide x to the third by x, or take one of the x's away, I have 2 left. If I divide 10 by 2, I have 5. There were 2 x's. I'm taking 1 away, so there's 1. 14 divided by 2 is 7. And then the x's cancel out. There's none left. So when you divide each of these by 2x, you get this.
Oh, this is where you take the best you can out of each of them, what they're late, and then you just divide it by that number? Okay.
Yeah.
Yeah, I remember everything.
It should, I mean, you've done this before. It's just... All right, now, here we don't have a common factor, so we need to actually factor this into 2 binomials, and there are 2 methods. I'm going to show you my favorite method first. It's the big giant X. Okay, and the big giant X works when this x squared right here, so it's ax squared plus bx plus c, and that is a 1. So essentially that it's not there. That's when the big giant X works. So, big giant X. I'm going to draw a big giant X. I'm going to put a multiplication sign there, and I'm going to put a plus sign here. All right. Now, the 6, or the end term, goes with multiplication, and then the middle term goes with the addition.
So that way the
Yes.
last term-
Yeah, the last term will go with your multiplication, always, and then the middle term will always go with your addition. And I am looking for 2 numbers that if I multiply them together, I get 6, and if I add them together, I'll get 5. Yeah, so like things that multiply to make 6, right, are 1 and 6 or 2 and 3.
Yes.
So I'm looking for the 2 numbers that when I multiply them, they make 6, but when I add them, they make 5. So the numbers I'm looking for are 2 and 3. And they're going to both be positive because everything's positive. And so this is factored out as x plus 2, x plus 3. Same basic principle, but see how this is negative but this is positive? I still am going to make the big giant X. I'm still going to do the multiplication and the addition, and I'm still going to put them together. You know, the 12 goes with the multiplication, and then negative 8 goes with the addition. Now, if This number on the end is positive and this number is negative. I'm looking for two things that when I multiply them, I get a positive number, but when I add them, I get a negative number. So I'm looking for two negative numbers, right? Because if I multiply negatives, I get a positive, but when I add negatives, I get a negative.
So like -2 or -6?
Exactly. Yeah. So I'm looking for two negatives, because if I say -2 times -6, I get positive 12, but -2 plus -6 gives me -8. Oh, that's not what I meant to do. This is negative and this is positive. What we have, we're still, like I said, still big giant X. But now we have a situation where I'm looking for two numbers that when I multiply them, I get a negative. That means I'm going to need one negative and one positive. And when I add them, I'm going to get a positive 14. So what I'm really kind of looking for is that the difference between the two numbers, if you ignored the signs, right, would be 14. It's still a sum, but one's positive, one's negative, so it's kind of a difference at the same time. Does that make sense? At all?
Is that what it said? Difference?
Difference, yeah. So if you think about, okay, two numbers that multiply to make 15, I can either do 1 and 15 or 3 and 5. If I take 3 and 5, I can't get a 14 out of that. But if I do 1 and 15, I can get a 14 out of that because the difference between 1 and 15 is 14. And I want my 14 to be positive, so I'm going to make my 15 positive and my 1 negative. Does that make sense? Okay. And so when I factor this, it's going to be x plus 15, x minus 1. Okay. It's kind of the same deal when they're both negative. If I'm multiplying to make a negative, I need one positive, one negative. And I want factors of 21 that have a difference of 4. So my factors of 21 are 1 and 21 or 7 and 3. Obviously, it's going to be the 7 and 3 because they have a difference of 4. I want the 4 to be negative, so that means I'm going to make the 7 negative and the 3 positive. X method, there's the old-fashioned way to do it, where you make factors tables. So I'm going to take the factors of 6 and their sum. Okay, so I have 1 and 6, and if I add those together, I get 7. I have 2 and 3. If I add those together, I get 5. As long as this matches that, I'm golden. So x plus 2, x plus 3. When we get into, say, we have factors of 12, and I'm looking for a sum of -8, well, I can start listing factors of 12, but if I start listing all positives, I'm not going to get a negative factor, right? So I start listing them all negative. 3 and 4 gives me a -7. -2, -6 gives me a -8. Okay. So then I found my match. So x minus 2, x minus 6.
The top one is 72. Yeah, does the top one say 72 or 12?
Oh, that's a 12. It just is it's an ugly one. There. With the factor table, if you have a negative here, you're looking for a negative and a positive factor. And so it's still going to be the factors of -15 in the sum. So if I say 1 and -15, I'm going to get negative 14. So if I do negative 1 and positive 15, I'll get positive 14. Which matches. So now I have my factors. So just, if your last term is negative, just make sure that when you're doing that, you keep in mind that it's negative. And so you have a positive and a negative factor. So if I did 1 and negative 21, I'd get negative 20. If I do negative 1 and positive 21, I'll get positive 20. Negative 3 and positive 7 gives me a positive 4. Positive 3 and negative 7 gives me a negative 4. That's what I was looking for. So those all work really, really well when there's nothing on the x squared, right? But then I throw this 6 in here and it makes it confusing. All right, so what you want to do is first, I don't need to write first, I wrote 1. Okay, so the first thing we want to do, if I have something on the x squared and it's not, if there's an actual number there, first I want to see, okay, is there anything I can factor out of all 3 terms? Okay, so I'm going to look at this. I'm going to say 6, 7, and negative 3. No. Sometimes there will be, sometimes not. Okay, but if there is one, you want to do that first because that makes all your numbers smaller that you're working with. And also sometimes the number you factor out might be this number, and then you're back to a situation with the big giant X. Okay. If that's not the case, you want to multiply the first and the last numbers. Okay, so I'm going to take 6 and I'm going to multiply it by negative 3, and that is going to give me negative 18. And then I'm going to look for factors of, wow, I can't write today. So now I'm going to look for factors of negative 18 that are going to have a sum of 7. All right, so and like I said, I'm looking for a sum to be 7. Now, you can either, at this point, use the factor table, or you can go back to the big giant X to find these 2 factors. So I'm going to list them both. Okay. Factors of negative 18. Well, 18 is 2 times 9, right? If I make the 2 negative, or the positive and the 9 negative, I get a negative 7. If I make the 2 negative and the 9 positive, I'm going to get a positive 7. So I'm looking for negative 2 and positive 9. Okay. Okay, now this is what I'm going to do. I'm going to take that positive 7 and I'm going to replace it with negative 2x and 9x. So now I have 6x squared minus 2x plus 9x minus 3. Okay? And what I want to do is I want to arrange these two numbers so that the first two numbers will have a factor I can take out of them, and then the second two numbers will have a factor that I can take out of them. So I wouldn't want to put the 2 with the 3 because there's not anything really to take out of those two together, so I'm going to put the 9 with the 3. Do you see how 6 and 2 have something in common? They have a 2 in common, and then the 9 and the 3 have something in common. Whereas if I put the 2x next to the 3, they don't really have anything in common. Does that make sense? So you want to, it doesn't matter what order you put these in as long as you have something in common.
Oh, so when you're putting them into an equation, or you're making them?
Yeah, when you're putting them, when you're replacing this with these two, you just want to put them in the order that you'll be able to factor something out. And now we're going to do factoring by grouping. So okay. So what I'm going to do is I'm going to look at these two and these two separately. First group, second group. And now I'm going to look at 6x and negative 2x. I can take and divide out a 2 and an x. And that leaves me with 3x minus 1. And if I look at 9x and negative 3, I can factor out a 3, and that leaves me with 3x minus 1. If you have done this correctly, these will match. Okay. So what I'm going to now do is I'm going to take these two numbers here and I put them in parentheses together. And then these two, I just write that down once. So I'm going to take 4 and multiply it by 25, and that gives me 100. And then I'm looking for factors of 100 with a sum of 20. Okay, so right now I have, well, if I did 2 and 50, I would have 52. If I do 10 times 10, that gives me, sorry, I'm multiplying, that gives me 20, right? So I'm looking for 10 and 10. So I'm going to take that 4x squared, and I'm going to replace this 20x with 2 10s. Because it's the same thing, right? 20x is the same thing as 10x and 10x. From this first set, I can factor out a 2x, and that gives me 2x plus 5. And then from this second set, I can factor out a 5x, or 5, and that gives me 2x plus 5. These match. So I'm going to take these two numbers and create a parenthesis out of them. And then I'm going to take the second parenthesis, that's these two. So I get 2x plus 5 times 2x plus 5, which if you want to go one step further, you can. And make it, I didn't realize I'd picked a perfect square trinomial. Yeah, I should have picked one. Want one more? Right. Yeah.
The 2x and the 5, what do you do with them when you're bringing down the 2x plus 5?
Here,
Yeah.
these came here. And then these two, because they match, become this one.
Alright.
this one will be a better example because they won't match. I'm going to take, okay, yeah, 11 times 7, and that's going to give me 77. And I'm looking for factors of 77 with a sum of negative 78. Well, we've got 11 and 7. If I did those both negative, that would give me negative 18. Or if I do negative 1 and negative 77, that gives me negative 78, right? So I have to replace the negative 78 with negative 1 and negative 77. I'll just put the 1 in there. Okay. From this first set, I can factor out an 11x. So I'm left with x minus 7. Now, this is a good example because I want this, when I factor something out, I want x minus 7. I want it to match. Right now I have negative x plus 7, but I want x minus 7. So I'm going to factor out a negative 1, because if I factor out a negative 1, it changes the signs. Does that make sense? Okay. And then I'll take these two, and that makes this first parenthesis. And then these match, so that's my second parenthesis. The normal notes. Perfect square trinomials. So if you square a trinomial, what you do is you have the first term squared plus 2 times the first times the second plus the second one squared if they're both positive, or if it's positive. Or you get the first one squared minus 2 first times second plus the second one squared if it's negative. So this is the pattern. So if we square this x plus 4, I get x squared plus 2 times 4 times x. Right, so 2 times 4 is 8 times x.
8x.
And then plus 4 squared, so that's 16. 2x squared is 4x squared. And then I want to do 2 times negative 3, which is negative 6, times 2x. So that gives me negative 12x. And then I do negative 3 squared, which is 9. Okay, so that's essentially what I did. Okay. So these are the steps to give us this. Now, a difference of squares is factor. We're going to factor. And whenever you factor difference of squares, so if you have a perfect square minus a perfect square, it factors to the square root plus and the square root minus. So I take the square root of the first one and the square root of the second one, and I plus minus them. So if, for example, I had x squared minus 4, perfect square, so that's x plus 2, x minus 2. If I have 4x squared minus 9, perfect square, these are the easiest ones to factor. You just take the square root and the square root. And a perfect square, And we'll go over the squares if you need them, but I look at this, I go, oh, 4 is a perfect square, 25 is a perfect square. So I'm going to test the theory. Okay? So what I'm going to do is I'm going to take the square root of each of these. And the square root of 4x squared is 2x, and the square root of 25 is 5. And then I'm going to test to see if it's a perfect square trinomial. I'm going to multiply those two together and multiply it by 2. So I get 2x times 5, which is 10x, times 2, which is 20x. If this matches this, you have a perfect square trinomial. Does that make sense? Okay. So you want to check to see if it matches. So take the square root and the square root, multiply those together times 2, and see if you get the same numbers here. If that's the case, you now have your factoring. If this is positive, this is positive. If this is negative, this is negative. And you already have your 2 factors. And then you just take this 2 and you move it over here. Do you guys want to see another one of those? Yeah? Okay. Let's do... Actually, let's do a minus. Let's do... Okay. I'm going to take the square root of each of these. So I get 3x and I get 7. And then I'm going to multiply those together and multiply it by 2. 3 times 7 is 21, times 2 is 42. Okay. This matches. This is minus, so this needs to be minus. Better? Okay.
The actual answer is 3x negative 7 squared.
Uh-huh.
You always multiply by 2.
Yeah, you always want to multiply it by 2 because the pattern is it's the squared
If it was
2.
3, would it be 3?
Hmm?
If it was 3, would it be 3? Like, what if it was, it says squared or cubed?
Cubed is different. And we'll talk about factoring
But you have to
cubes
do the,
later. There's a formula for it. There's a formula for factoring cubes.
I'm trying to think of what it is, but I'm not
Yeah. We're not there yet. Don't worry about it. And we already did this one, but we'll just do it again. Take the square root and the square root. Square root is x. The square root is 2, so I'm going to do x plus 2 and x minus 2. So whenever you have 2 terms and they're a difference, if you have just a something minus something and you're told to factor it, see if they're perfect squares. If they are, take the square root of each and do this. Now, can I factor this? Okay. The reason this works with this minus on it is because if I FOIL this back out, I get x squared plus 2x minus 2x minus 4. And so that plus 2x and that minus 2x cancel each other out. If I were to try to say factor this out in the same method or something, but maybe with pluses, you'd actually have a perfect square trinomial. So it would actually be x squared plus 4x plus 4. So if you have 2 terms and there's a positive sign between them, it doesn't matter if they're both perfect squares, this can't be factored. It can only be factored if it's a difference of squares. Okay, so don't let that trip you up and confuse you.
don't you do 1 over 3 or something?
Comes to